welcome back to the next lecture. And this is gonna add another connection in the topic of convolutions into the algebraic side of the problem. And we are gonna talk about some idea which originates in this idea of additive combinatorics. And here in particular we are going to talk about something called sumsets in the group ZP and relation to convolutions. So this is in the lecture notes, the section after when we talked about the transfer operators and their connection to the convolution, and now we'll just add something about this sumsets. So the basic idea here is that if you remember with the convolution, let's say we had this random walk and we kind of start from a circle over here. We can 0, 1, 2, 3, 4, 5, 6, 7, and then we have like 8 elements here. Then when we start to walk with random choices, let's say with some probability, we go back and forth, possibly like on here and so on. And we have all the possibilities that could come in here. And then the convolution was something that when you started, let's say from a probability distribution mu, and you start expanding that, like taking higher order convolutions, you will see that this starts to spread around the group. So we will end up to a situation where you're basically spreading out the mass of the measure around the whole group. So let's say if you start from something which is quite concentrated on a couple of the points in the group, then the convolution operation will flatten it. It will start to converge towards maybe to hopefully to the uniform distribution or something like that. But there are some obstacles in the group theory which are called subgroups. And the subgroups cause the issue that they can trap the random walk within them. So they're like subspaces that can trap the dynamics into them. And later on when we talk about some notion of like ergodicity and mixing of random walks, we will see that these are the kind of possible obstacles that would come for the mixing of the random walk. And here the idea about sumsets, how is this all coming back into sumsets, is that the sumsets describe of the points where the convolution would spread into. And if you would continue the like several iterated convolutions for a long time, you would end up like spreading around inside these sumsets. So for that purpose, we defined if A and B are subset of set B, then their sumset is just the set of all possible sums. So that's just A plus B. Maybe I should use T and S, T in A and S in B. Okay, so the sumset is formally something that captures some properties of the original sets A and B. And there is some like basic properties, and these are on the notes as well, that I've said that, for example, the maximum of A and B, the cardinality, so this is the A is the cardinality of A, or the number of elements in A, then this is at most the cardinality of the sumset. So just these kind of relations to this, and then of course the product of these two. This is the maximum number of elements that could appear in the possible combinations of two elements when you sum them. Then the other property that we have, of course, is this one thing to maybe consider is as a corollary basically of the above, that if you have the same set, then the sumset with itself is then at most A squared and then at most A. So it's between these two values that you kind of see if you have the same set. So that's kind of one of the basic properties. And then like there is kind of like deeper connections. So it's possible that the minimal thing might happen or the maximal thing for some set A. This is all possible that could happen. Okay, so let me give you like an example that would like highlight the situation where you could actually achieve the kind of possible maximal situation that you have in here. Then one example where this kind of appears in the possible sums is like, let's take A to be equal to this 0, 2, which is a subgroup of Z4. So we are just considering the case Z4. And now if you take A plus A, what we obtain that is actually all the possible sums that you get here are just the A itself. So there's nothing happens when you add the sumsets to itself. So this means in particular that A plus A has the same cardinality as A. But for example, alternatively, if we take, I don't know, let's take A to be, I don't know, I think 0 and 1, which is not a subgroup, then we get that A plus A, which is all the possible elements. So we of course have 0 and 1 there, but we also have like 1 and plus 1, which is 2. So we also have 0, 1 and 2 in this set when you add all the possible sums. And so we get that the cardinality of A plus A is actually this is A plus 1. So it actually is almost something got added into the sum. And in the maximal possible case, like you would only at most get like the A squared. So that's something that could maximally happen in this situation. So so that's like kind of the philosophy here, that in some sense, if you have a subgroup, so this is not a subgroup, this one, but this is a subgroup, then you expect this kind of phenomenon to happen. And why this is important in our situation is that we will see that the convolution of the measures that define the random walk, there's something called the support will be the sumset. So if you don't add any elements when you're like taking the convolution, which is meaning you evolve with the random walk, you're getting stuck and more stuck inside these subgroups. And later on we can see also like in the random walks and groups that kind of the thing that kind of is enemy for something called mixing, which we will talk about later, is really the when we are getting trapped to subgroups, or we are like trying to concentrate around subgroups. So one other property which maybe I could mention that's the lower bound, which is called something called Cauchy-Davenport inequality. Which says the following, that if P is prime number, then this for any A and B in ZP, we have that the A plus B is actually bounded from below by minimum of A plus B minus 1 and B. So there's some improvement that you could get, and this is not in the lecture notes, the proof of this, but I put a reference if you want to see the proof of this. It's an improvement over this trivial inequality that we have here. So there's something to which allows you to bound these things from below. So the connection to sumsets and the convolutions comes from this idea of support. So the definition, what we want to impose here is this something called support of probability distribution. So what we define is that if mu in ZP to 0, 1 is a probability distribution, then we define the support, we call it SPT mu, is just a set of t's in ZP such that mu t is positive. So it actually has some elements inside the thing. So that called the support of the probability distribution. Now the main theorem kind of in this section that I wanted to highlight is this basically saying that if you take the support of a convolution of two probability distributions, then it's equal to the sumset of the supports, mu plus, and then SPT mu. So this is the, in the notes I think I put it as a theorem 3.14 in the current version. And basically it's just saying that if you take the support of the convolution, we see this kind of sumset appearing. And let me give you the, let me see about the time. I think I could give this as a proof. So let me actually prove this, because this is interesting. You can kind of see how this comes into play. So let's give you the brief proof of this property. And so basically it's we are asking whether two sets are the same. So we can first prove the inclusion, which means that so we first let R to be an element in the support of mu star nu. And so that in particular means that the mu star nu of R is positive. And but on the other hand, the definition of the convolution, so this one over here, which is positive, we know that this is equal to S in ZP, or when the mu of the R minus S nu S is, so that's the definition. So this is positive if and only if, so the only way that this could be positive if this mu R minus S nu S is positive for some S in ZP. So because it's R is in here, which is positive, then we know that there exists one of those elements. So, but this is possible if and only if mu R minus S is positive, and they both have to be positive, otherwise it's impossible for the product to be positive. So these both have to be positive. And so in particular, if this is positive, then means that S belongs to the support of nu, for that one. But then defining T to be equal to this R minus S, we also obtain that mu of T, which is now this mu R minus S, this is also positive, that's the definition. So this T has to belong to also in the support of the measure mu. So we just obtained that R is positive, so it belongs to this set, but the main thing is that if you write the R, then R is equal to R minus S plus S, that's the just the definition. So R minus and plus S, we add and subtract the S, and then this is T plus S, and so this belongs to SPT mu and plus by the definition SPT nu. So this is all okay. So for any arbitrary element in the support of the convolutions, we actually obtain an element in the subset. And then for the converse, we can do it as follows. So if we take T plus S in SPT mu plus SPT nu, so these are like two elements in the and then we want to prove that the mu star nu, so the convolution at T plus S, is positive. Then then of course the t plus s belongs to spt mu star nu. So that's what we want to prove over here. And this is like now just using again the definition of the support. So what we do is that we just compute. We get mu star nu at this t plus s. If you open the definition of the mu star nu, this is just the summation over, let's say, r in zp and mu t plus s minus r nu r. That's the definition. So so that's what happens on this situation. So okay, and then now let's try to see that what if like this would be 0. So let's say this is equal to 0 over here. So this is like an assumption. So we want to basically prove a contradiction that if this is equal to 0, we get something that is equal to 0. So if this is equal to 0, so that's what we don't want, then this implies that of course they all have to be equal to 0. So that implies mu t plus s minus r nu r have to be equal to 0 for every r in zp. So now there are two cases when this is possible 0. So the case 1 is that mu t plus s minus r is equal to 0. And what happens in this kind of a situation, that if this is equal to 0, then of course the if we choose specifically, so this is the case equal to this is for all r, and let's say this is in the case that this happens for some r, and if here r is equal to s, then what we obtain that mu t plus s minus r, which is now this is equal to 0, this is then equal to mu t, which is then impossible because the mu t t was in the support, so this is not possible as the t belongs to the support of mu. So this is like one of the cases, and because we could choose that possibility. And the other case, case 2, that I want to consider, is that if at the moment here nu r is positive, is 0 for some r, for some like in this product. And then in this case, if we have this this property, then that implies that if we again study the case r is equal to if here r is equal to s, then we obtain that nu s, which is nu r, this is 0, which is not possible as the s belongs to the support of nu. So in both cases we got a contradiction if we assume that r is equal to s in this here. But this is now covers everything, because what we had here that this property holds for every r. So in particular it holds for r is equal to s. So if you use the r is equal to s case, in both cases, no matter which one is 0, it in both ways leads to a contradiction. So that implies that the logical conclusion has to be that mu star nu t plus s, which is we got, has to be positive, which proves the claim. Okay, so that was everything I wanted to tell you about sumsets for now. Just to maybe recap a little bit. So the main idea with this theorem will be that if you want to basically connect some of the ideas from random walks into the group theory, this is the main theorem that allows you to do that connection. You start, for example, if you're able to prove some nice, interesting properties about subgroups of some complicated group, and you get some kind of results about their properties, then, and you have a question that relates to maybe random walks on these groups, then this is a theorem where you could use this to like understand what the supports of the convolution should look like. So then you have an idea about the mixing properties of the random walks, for example. So I'll leave this for now, and there's some other exercises in the notes that like computing different kind of supports of convolutions, which I leave for the next thing. And in the next topic, I will plan to go through more into the probabilistic intuition and of the sumsets, how they come, and how the convolutions model the random walk. So that's all for now. Thanks.